Alright, this is lecture number 15, I believe. So, in this lecture, we're going to start the material which probably goes beyond what you learned in Math 125. But before we do that, let me show you this flowchart and explain what that means. Okay? So, this is very useful flowchart that we're going to be using for the rest of the semester, and it's going to be very useful too, actually, on your final exam. Well, this chart, in a sense, represents the entire course. That's basically statistics, BUSN 231, business statistics. For the most part, that's what we're going to be doing. I mean, some tests that you will see on this chart we will not use, but a lot of tests from this chart we're going to discuss them in to a different degree of details in our lecture. So let me explain what that means. First of all, I personally view statistics as just a bunch of tools. So this is a tool set essentially. It's a tool set to analyze the data, and we discussed earlier in this semester that statistics operates with three different data types, right? Data can be either numerical, also called interval sometimes, right? Or categorical. And categorical comes in two different flavors. There is ordinal data and nominal data. So both of these data types are just a bunch of categories, so they're not numbers from that standpoint, but oftentimes we assign numbers to them just to make things easier to record. And these numbers serve as just simply labels, right? So we can say Republican is 1, Democrat is 2, married is 1, divorced is 2, single is 3, widowed is 4, that kind of stuff, right? Okay, so three different data types. And also, we are looking at investigating different aspects of data. For example, everything that we've done so far was revolving around you have one column of data that's coming from one population, okay? And if the data is numerical or interval, then we're going to discuss, for example, hypothesis testing, right? So in the previous couple of lectures we discussed three different examples. The average account balance in the accounting information system, is that above $170 or is it not? Or the average number of customers at the drive-up window at the bank, did that go down from 20, its previous historical value, or did it not? Okay, so these questions were evolving around the location of the center of the data, right? So in all these hypothesis testings we discussed it was formulated, all these hypotheses were formulated as some statements about the population mean, the true population mean, which we will never know, right? We discussed that. The only thing that we have about population is the small subset that we call sample, okay? In a different example that we discussed at the end of the previous lecture, we looked at categorical data, right? Customers of State Farm Insurance, what percentage of customers say that they're satisfied with customer service, right, provided by the insurance company. And we again tested the claim about true population proportion. So if you look at all customers, 100% of them, and ask every single one of them, are you okay with services provided by State Farm Insurance? Certain percentage of them will say yes, and that's what we were testing, right? It was a statement, alternative hypothesis was a statement about true proportion in the entire population of customers of State Farm Insurance. So it was similar kind of to the testing of the mean, and different at the same time, because we're not talking about the average, we're talking about proportion, right? And everything that we've done so far was revolving around analysis of one single population. So here is the structure of the course, really. So on this left side of this analysis flow chart. So in this course we're going to be dealing with 5 different big topics. Topic number 1, which largely we already discussed and covered, so we're pretty much done with that. Describe a population, meaning a single population of data. We've done that, right? We discussed how we can test hypotheses about population mean in case of numerical data, or population proportion in case of categorical data. And also, before we looked at hypothesis testing, the point of our discussion was confidence interval. Now, confidence interval is just another way to make statements about the population mean or population proportion, right? Depending on if you have a numerical data or categorical data. It's just another way to estimate what the mean can be and what the proportion can be. So we're largely done with this topic. Next topic that we're starting actually in this lecture today is we're going to be looking at comparing two different populations. Okay, so in other words, you have two columns of data now, and each column comes from different population of data points, different set of observations. Okay, and again, we're going to be comparing either means if it comes to numerical data, or proportions when it comes to categorical data. Then after that, we're going to expand that. We're going to say, okay, how about, can we compare in one single test more than two populations? So all these cases are coded, as you can see, in yellow color, right? We're going to be discussing actually a lot of these tests. And then after that, we're going to analyze relationship between two variables, and at the same time relationship between two or more variables. So specifically, and in these two different topics, actually I kind of see them as combined. Analysis of two variables at a time, we're going to largely concentrate on linear regression and correlation between x and y, two variables. When we discuss analysis of a relationship between more than two variables, we're talking about multiple regression. Okay, so this is going to be our primary focus in these two last topics. And also, if you look at the way how each one of these trees, so each one of these big subtopics, right, in our course is organized like a tree, top-down tree. So, for example, describe a population. Let's take a look at what we already did, right? What data type you have, and as you can see, each one of these trees, the very first question that you have under the root, right, of the tree is, what is your data type? And it always branches in three different directions, right? Data can be numerical, also called interval, or categorical, ordinal or nominal. So let's say, for example, I have a numerical data about our last problem, right? Bank customers. So bank saw the competition to open up right down the road, and they're afraid that competition will lure the customers away from them, so they will see less of the business, right? So in this case, when I see one column of data, I'm going to say it's about describing a population. Data type is interval, so I'm going this direction. Type of descriptive measurement. So you can see that I can either test hypothesis about the central location or about the variability. Now, disclaimer. You can see the same exact question in this one, right? Comparing two populations, data type, interval. What are you doing? Are you talking about central location or variability? So in this course, we're concentrating on the data center. So our hypotheses are always going to be either about the mean, what we've done so far, or about the median, what we didn't do yet, but it's coming later on. We're going to take a look at the non-parametric tests. Okay, so we're not going to even touch the variability. So therefore, that portion we're not going to discuss. Variability, that portion we're not going to discuss. Other than that, we're going to discuss actually a lot of these tests. And so coming back, right? So I see one column of data. So it's describe a population. What's the data type? Interval. What are you doing? Looking at the means, central location, or variability, variance and standard deviation. Well, we're talking about central location. Is mean number of customers less than 20? Now that our competitors opened up a bank down the road, and then you arrive to the bottom of this decision tree, and it says, well, if that's the case, you're talking about single population, interval data, you're looking at the central location, then you're going to have to use t-test to estimate the mean mu. Okay, t-test, an estimator of the mean mu, such as, for example, confidence interval. Confidence interval is the estimation, it's the interval estimation of the mean mu, right? So essentially what I'm saying is this: each one of these different decision trees, it starts at the root, right? You need to kind of decide for yourself what are you talking about in this problem. Are you looking at one population, or two populations, or three and more populations? Or is it about relationship, right, between x and y? Or is it about relationship between between y and multiple x's, so three or more variables? So depending on how your problem is structured, you will start at one of these three, what am I saying, five different root nodes, right? After that, you have to kind of come down one step and decide what type of data you're dealing with. Is it interval, ordinal, or nominal? Numerical, ordinal, or nominal? Then you have to decide, for example, for data type, right here, two populations, data type, interval. Sometimes you will have to ask yourself this question: how are the samples? So I'm talking about central location. Next one is, what do I have? Do I have independent samples or matched pairs? Let's say I have independent samples. The next question is going to ask you about testing of the normality. Are samples normally distributed or not normally distributed? And depending on the answer to this question, normal or non-normal, you'll end up with different tests, right? You will have to use either t-test to evaluate mu1 minus mu2, or, according to this flowchart, Wilcoxon rank sum test to evaluate the position, the relative position of medians, for example, okay, population 1 versus population 2. So what am I saying is this: at the bottom of all these decision trees, you have a listing of all possible tests, right? T-test for the single mean, t-test for mu1 minus mu2, Wilcoxon rank sum test, Wilcoxon signed rank sum test, sign test, z-test to evaluate p, one-way ANOVA, Kruskal-Wallis test, Friedman test, etc., etc. So essentially, that's what statistics is. It's a bunch of different tests, but the challenge is that we have to know which test is appropriate for which situation. And number two, once we pick the test, we have to be able to use this tool, right? So coming back to my analogy, statistics is a tool set, right? For example, if you have two populations of numerical data, depending on how the data was collected, is it independent samples or is it matched pairs, you're going to have to use either independent samples t-test or matched pairs t-test. But that's only if the data samples are normally distributed. What if they're not normally distributed? Both of them or only one of them, which is already enough for non-normality. Well, then you have to pick between that tool, Wilcoxon rank sum test, and Wilcoxon, this one, Wilcoxon signed rank sum test. So some tools, each tool is appropriate for each specific data type or each specific situation. And that's what we're going to be doing for the rest of this semester. We're going to be learning essentially all these different tools. T-test for independent samples, t-test for matched pairs, Wilcoxon rank sum test, sign test, one-way ANOVA, linear regression, multiple regression, Kruskal-Wallis test. We're going to discuss all of these tests, and that essentially will give you the picture of the entire tool set. Okay, so under different scenarios, different test is appropriate, and of course you will also learn how to use each specific test, how the test is formulated, then how do we perform the test in a program. We're going to use, of course, our R and R Studio, right, in order to run each one of these tests, and at the end you will get a p-value, just like what we saw in the last several lectures, right? Each test finishes and ends up with a p-value, and the p-value you compare against alpha, and then that's when you make a judgment call. If p-value is less than alpha, you always reject null. If p-value is higher than alpha, you keep the null. And after that, we received the answer to our business problem in terms of the statistical response, right? So in statistical language, your answer is going to be, okay, we either reject the null in favor of alternative, or we fail to reject the null in favor of alternative. But after that, we have to convert the statistical answer in business terms. Like, what does that mean in terms of the actual problem that we were trying to address from the get-go to begin with? Okay, so we're going to be referring back to this flowchart a lot during the rest of these lectures, and you will see as we go through more and more material. So it will start to become more and more systematic understanding of what is the tool set that is statistics when it applies to the business problems, and how to use each and every one of these tools. Okay, so with that in mind, let's switch over to our next lecture. So we're starting next topic, and that would be comparing two populations. So, like I said, everything that we've done so far was revolving around one column of data that comes from one population. We looked at two different types of problems, right? In first type of problem, we're dealing with numerical data, and we were looking at confidence interval and hypothesis testing. But all of that was about the population mean, right? Again, we never are going to discuss statistical tests or confidence intervals for the variance or for the standard deviation. Okay, so this is not part of this course. Everything that we're going to do will be about measures of central location. Well, with the exception of linear regression. In this case, we're talking about is x related to the y in a linear way. Okay, so it's about relationship between two variables. Aside from that, everything else is going to be about central location. So when we discussed one population, it was either numerical data, in which case it was the mean, or it was categorical ordinal nominal data, in which case it was population proportion, right? So starting today, we're going to look at multiple different populations and our ability to test them at the same time. So what are the applications of this material? Actually, there are a lot of them. For example, in the business scenarios, right? I always discuss at this point marketing example. Why companies do marketing? Well, companies invest into the marketing campaign hoping to increase the sales, right? They increase brand awareness, or they advertise certain specific product. The hope is that as we spend dollars on marketing, we will see increase in sales and therefore increase in profits as well. Okay. Now, from that standpoint, what makes sense for me to do is this. How do I know that my marketing campaign has achieved the goal? So I hope that my sales will go up. All right. Now, question: is that possible that I advertise, I run the marketing campaign, and in some places my sales will actually go down? Yes, it is possible, right? For what reasons? For a number of reasons. Sales probably depend on a lot of factors, right? My advertising is not the only factor that drives my sales up or down, right? My competitors can be even more aggressive in advertising, right? That can be a factor. Or in some places, it could be like weather. Weather is also a factor. What happens when it rains or snows outside? People tend to not go to the stores, right? So even if I advertise in some regions, I may experience drop in sales because the weather was kind of nasty and people chose to stay at home, not to go to the store, that kind of thing. So therefore, if I want to compare the averages, right, if I want to evaluate the effectiveness of my marketing campaign, probably the question that I want to ask is, are the average sales before lower than the average sales after I advertise? If that is true, the true average before the advertising is less than the true average after the advertising, then my marketing campaign did achieve the goal, right? So I put a commercial, I see the increase in average sales, and I say, well, that was a successful commercial right there. Okay, so that basically is one example when comparing two populations of data could be of business value. All right, now here is another something. Each time when we're going to run the hypothesis, we're going to always formulate that in terms of average for the population number 1 minus the average for the population number 2, if data are numerical. Or, if we're dealing with categorical, ordinal, or nominal data, it's going to be proportion for the population number 1 minus proportion for the population number 2. Here is an example. Popularity vote, right? Popularity rating before and after the election. So what happens oftentimes is the approval rating, right? That's another term for this thing. Approval rating. Approval rating of a person, or like president, it oftentimes goes down after the elections, right? Because he was promising a lot of things before he was being elected, and then elections are over. So now it's like, yeah, it's not actually that great. So approval rating goes down. So how can we know if the approval rating before the election is higher or lower than the approval rating after the election? Same thing, right? We're going to collect two different sets of numbers. So, like for example, right now we're kind of not too far away from the next elections, right? So if we ask people, do you support the current president? Then we can record the answers yes, no, right? That's really what it boils down to. Categorical data. Do we approve? Yes, I approve. No, I don't approve. And we can collect a bunch of responses, let's say, I don't know, 1,500 of them, and record before the elections. Then elections happen, and we're going to couple of months, 3-4 months down the road, right, after the person was in the office, we're going to collect same data one more time. We're going to say, well, what about now? So you were telling me yes, no, when the person was just a candidate, right? Do you approve him as a candidate? Like, is what he's saying, does it sound good to you, right? Now that the person was in the office for some time, what do you think? Is it still yay, or is it kind of not so great anymore? Then again, we're going to ask people, do you approve? Yes, no, and we record the second column of data, right? And in order to see where the approval rating go, where it went, did it go up or did it go down? Again, we're going to perform the hypothesis testing, but it's not going to be proportion 1 versus proportion 2. It's going to be about proportion for the population number 1 minus proportion for the population number 2. Okay, so, and the assumption again, just like what happened with our single population analysis, is we do not know anything about any of the two populations. We don't know the mean, we don't know the standard deviation for any of them, or in case of categorical data, we don't know the actual proportions, right? So again, our evidence, remember our discussion how hypothesis testing is similar to the criminal proceedings in the court, right? In the court, you have evidence presented in front of jury, and then jury decides, do we stick with null hypothesis, the defendant is innocent, or do we change our mind and now go with alternative that he is guilty, right? Same thing here. We're trying to decide what something about difference, mu1 minus mu2 or p1 minus p2, right? And our evidence really comes in form of two samples now, right? We have sample from population number 1, sample from population number 2. So we have to evaluate this evidence and see what does that mean. Okay. So let's discuss. So in this lecture, we're going to concentrate on comparing of the means for the two populations of numerical data. Okay, so therefore our discussion will revolve around mu1 minus mu2. But before we get into the nitty-gritty, let's discuss how the data are collected. Right. So the idea is very simple. You have population number 1, you have population number 2. That's everything that you wanted to know. But we discussed that statisticians don't use really all the data, oftentimes because they can't get it, right? And they settle for samples, right? So from population 1 you get sample 1, from population number 2 you get sample number 2, and that's our evidence really. The sample sizes don't have to be the same. Generally speaking, they can be different, right? So here we have N1 items from population 1 and N2 items from population 2. They can be different in case your samples are independent, okay? Speaking of independent samples, so in this lecture, that specific lecture today, we're going to discuss the case when two samples that you collect from population 1 and population 2 are independent. So what does that mean? That means that sample 1 is random. So for example, let's go back to our discussion of marketing, right? So I conduct marketing campaign in order to see if my sales, the average sales per store, will go up after the advertising, right? So if my samples are truly independent, here's what probably can happen. Let's say I'm running a retail chain, such as Walmart. That's kind of extreme example, but let's go with it. Walmart has a lot of stores, right? Pretty much everywhere. So what I can do is this. Before I conduct advertising, I pick, let's say, 150 Walmart stores, okay, randomly, out of however many. They have probably close to 3,500 stores, I'm guessing. And I'm going to pick 150 stores completely randomly, okay? They will end up in different states, in different localities. They will have different size, right? So, and then I'm going to forget about this first sample that I collected. So I'm going to record, of course, average sales per week, so everything that I need to know about this first sample. Then I'm going to forget about my first sample. I'm going to set it aside, and I will conduct the marketing, advertising, and after that, sales will either go up or go down, whatever will happen after I advertise, right? And then I'm going to collect a second sample. Since I don't have any recollection about my first sample, I kind of put it on the shelf for now, right? I'm going to pick a different sample. It doesn't have to be same. It doesn't even have to be 150 stores. Let's say now I want to collect 200 stores, right? So I pick 200 observations, and again, I don't even know what stores ended up in the first sample, okay? So in my sample number 2, after I advertise, I may end up with some of the stores from the sample number 1, right? So, and some of the stores will be that are not from the first sample. They're new, right? I didn't look at them before. So that is how I collect the data as independent samples. So sample 1 and sample 2 have nothing to do with each other. Alright, so this is my first way of collecting data. Now, if the samples are not independent, then they are what? They are dependent, right? Or in statistics, it's also called matched pairs, oftentimes. Okay, so let's discuss how exactly the matched pairs data are collected. Let me first say that when I pick my first set of stores randomly and my second set of stores randomly, there may be a lot of different things that get into the mixture that will affect my results. For example, let's say I'm going to have some stores are large, like for example, in the cities, big cities, such as, I don't know, Chicago, right, or Boston. You can't really, or Atlanta, you can't really put a huge Walmart store in the middle of the city, right? If you ever been to Georgia Tech in Atlanta, Georgia, there is a pretty big and good university called Georgia Tech. I was there once, and right there on campus they have actually a Walmart store, but this is just like a mom and pop store. So it's not this huge freaking Walmart that you're used to. It's really a very downsized store. Okay, so Walmart is really small. Well, just because you can't put a large, box store in the middle of the metropolitan area, right? So it could be that my some of the stores that I randomly picked in my sample number 1 or sample number 2 will be just different in size, purely randomly, because my selection is random, right? So the fact that sales are lower in one store, that may not necessarily be a reflection of the fact that advertising is not working, right? Maybe due to the fact that the store is smaller, simple as that. Advertise all you want, right? If the store is small, you're not going to generate a lot of sales out of that, okay? So therefore, comparison would not be 100% accurate, because it's not just the effect of advertising that will play into the difference of sales, but it's also effect of locations, right? Some stores are in densely populated area that generate a lot of sales. Some store in the sparsely populated area that just inherently get less sales, right? With or without advertising. So if I want to exclude all these other factors that may get into the mixture, and I want to study the effect of only advertising, here's what I need to do then, okay? My first sample from population number 1, that would be before advertising, should be completely random. So I pick 150 stores at random, and that's it. After I do the advertising, and I record the weekly sales, right? That's my population number 2, that's after, right? But I do not pick the second sample randomly. Instead of that, I match each observation in sample number 1 with each with just one observation in sample number 2. More specifically, in my case, I'm going to be looking at the same store, right? So this way, I'm excluding factors such as geography, population density, this type of stuff, right? So now I'm looking at store versus the same store. Difference is one number is before I was advertising, and another number is after I advertised, right? So that's basically how dependent samples are collected. Sample number 1 is random, sample number 2 is hand-picked. It's matched, each observation in sample 2 is matched with exactly one observation from sample 1 by using certain characteristic. For example, in this case, it was the same store, right? I was looking at the same store before and after the advertising. And each time when we're going to discuss the problem with matched pairs or dependent samples, what is that makes the two observations click together or matched, is going to be different. And you will see in examples that we will discuss in class what exactly is that each time. Okay? Alright, so here is the idea behind the hypothesis testing for two populations. As I was saying before, the evidence comes from samples, right? So we are going to look at sample number 1 and sample number 2. Eventually, at the end of the day, we're going to evaluate the test. We're going to evaluate the difference. Average for the population 1 minus the average for the population 2. But since we don't have any of the population's data, we're going to have to settle for the sample averages, right? So our difference between x bar 1 and x bar 2 coming from the sample will be the best estimation, the best shot, right? How we can estimate what the difference between the population average 1 minus the population average 2 really is, okay? And based on the amount of this difference, how far away my sample 1 minus sample 2 averages, we're going to judge is there really a difference between mu1 and mu2. Okay, so if x bar's difference between x1 bar minus x2 bar is large, I'm going to say, yeah, likely it will point to the big difference in the sample 1 minus sample 2. Okay, otherwise, if this difference is not so large, right, then probably mu1 and mu2 are close, maybe even the same. And the reason why we're going to do the we're going to have to do the test is variability. Every time when we test the populations, statements about mu population or mu1 minus mu2 population mean differences, the reason why we can't say for sure is because of variability, right? Each time when you pick a sample, it comes from a sampling distribution. Could be pretty much anywhere around mu1, okay? Same is true about the population number 2. Your x2 bar is coming from the sampling distribution, which is centered around mu2. And the fact that there is variability, that's what makes the hypothesis testing so tricky. Okay, if all the numbers were the same, we wouldn't have hypothesis testing. We would just collect a bunch of numbers from sample 1, sample 2, calculate averages, and say, yeah, clearly average 1 is higher than average 2. So there you go, here's your answer. But because there is variability, and sample average 1, sample average 2 are going to be different, each time you pick a sample, that's what makes it challenging. Okay. All right. Anyhow, so here's what we're going to be testing in everything that will happen next. Remember, we discussed 2 or 3 lectures ago that hypothesis testing takes 3 different possible forms, right? It can be greater than a number versus less than a number for the alternative, or less than a number greater than a number for the alternative, or equal for the null, not equal for the alternative. Well, guess what? Same exact thing applies to the comparison of the 2 populations. The only difference is that when we were talking about one column of data in the previous 2 lectures, it was always mu equals to certain number versus not equal, right? Or mu greater than or less than a number. Well, here, because we're going to test everything in this chapter, we're going to test in the form of mu1 minus mu2, so it's never going to be mu1 greater than mu2 or mu1 is less than mu2, that kind of stuff. It's always going to be about difference, mu1 minus mu2. So same 3 forms, they still hold, okay? Greater than a number, less than a number, greater than, equal to a number, not equal to a number. The same 3 forms as before. But now instead of the mean, you have mu1 minus mu2. Okay? So, let's kind of quickly go through these couple of slides because I don't want to get into the nitty-gritty. The way how the tests are performed is this. x1 bar, as you know, we discussed that in sampling distribution topic, right? What's sampling distribution? Distribution of all possible sample averages. And we discussed that if you have a large enough sample, large enough means that sample size is greater than 30, then the distribution of your population is not really important. You know that each time when your sample size is higher than 30, your sampling distribution is going to be normally distributed. Okay, so that means that my first x1 bar is distributed around the true population mean mu1, and its variance is going to be sigma 1 population 1 variance divided by n1, or in other words, the standard deviation is going to be sigma 1 divided by the square root from n1. n1 is the sample size. Same applies to my sample number 2, right? I pick n2 numbers from population number 2, calculate sample average. I know that all possible sample averages form their own sampling distribution, okay? And the mean is mu2, same as population 2 average, and standard deviation is sigma 2 over square root from n2. The reason why the hypotheses about 2 populations are tested always in the form of mu1 minus mu2 is because if I take sample 1 average minus sample 2 average, since both x1 bar and x2 bar are normally distributed, there is a well-known property in statistics. Difference of 2 normally distributed variables is also a normally distributed variable. So x1 bar minus x2 bar is normally distributed with an average of mu1 minus mu2, so true population mean difference. And here is the variance. So variance number 1 plus variance number 2. So if you take square root, then the standard deviation is just simply variance number 1 plus variance number 2 square root. Okay. Now, from that standpoint, I know that x1 bar minus x2 bar, if I do the normal transformation, standard transformation, right? x1 bar minus x2 bar minus their true average, mu1 minus mu2 divided by the standard deviation. That's going to be a z-score, right? It's a standardly distributed random variable, standard normal. The only problem is I don't know sigma 1 and sigma 2. So what's my best shot? It's sigma 1 and sigma 2, the standard deviation for population 1 and population 2. It's the sample, S1 and S2 standard deviation, right? And if you remember from our discussion about 3 or 4 classes ago, if I don't know sigma and I replace it with a sample, standard deviation S, what happens is I have to replace the Z distribution with a T distribution, right? So therefore, we're going to use again t-test actually. So a big reveal, I guess, at that point that I have to tell you is we're going to use exactly same function to test two populations, mu1 minus mu2, as we did for one population. It's going to be the function t.test in R Studio. Okay. So here is one important thing, I guess, that we need to check each time when we perform the hypothesis testing. Okay. If you remember, each time when we tested the hypothesis about the one population mean, we had 3 examples in previous 2 classes, right? It's about accounts, average balance. It was about the average number of days that the skier spent in the mountains, just doing, just skiing, right? And the last problem was about, bank, right? Bank customers. Bank has a suspicion that competitors down the road steal away some of their business, and each time when we tested the hypothesis about the mean, we tested the single column of data that we had for normality, right? So, and we used 2 different tests, right? First, we looked at the histogram. Histogram is bell-shaped, then we're going to say, yep, normally distributed data, or so it seems. And then we also used the rigorous test, statistical test, which is called Shapiro-Wilk test, to get a statistical confirmation that yes, actually things are normally distributed. Now, in this case, when we are dealing with independent samples, we have to test each of the samples for normality. If one of the tests does not pass, if one of the samples does not pass the normality test, that means that oopsie daisy, we cannot use a t-distribution. Okay, so it can be both samples are non-normal, they're either very skewed or bimodal or trimodal or whatever they are, right? Or only one sample is normal, another is not. If at least one of the samples is normal, other way around. If at least one of the samples is non-normal, then we cannot use the t-test, and we have to go with one of the non-parametric tests. But non-parametrics we're going to discuss at the end of this semester. So for now, an important thing to remember is each time when you're comparing 2 samples of data that were collected independently, that's a keyword here, independent samples, okay? Then you have to test sample 1 and sample 2 for normality. Okay, so without further ado, let's get down to the brass tacks, so to speak, right? Thorndike Sports Equipment. It's the kind of cute problem. Let's read through that. Thorndike Sports Equipment has submitted a bid to be the sole supplier of the swimming goggles for U.S. Olympics team. OptiView has been supplying goggles for many years, so their current supplier. And the Olympic Committee says that it will switch to the new supplier, Thorndike, the contender, right? Only if their goggles are found to be significantly better in a standard leakage test. So what is that? To perform the test, they pick 50 goggles from manufacturer number 1, Thorndike, and 50 goggles from the manufacturer number 2, OptiView, and they put them on the on a dummy, right? On the mannequin, sort of, right? Surface that simulates the face of the swimmer. And then they basically start submerging these the goggles, right, under the water. So important thing, I guess, for swimmers is that the water, so the goggles form kind of a tight seal with the face, right? So that the water does not leak inside because you can't really see, right, anything. So, but, goggles eventually will start leaking, right? So what they do is they measure the depth, how deep was that in the water, at which the water leaking starts, and therefore the view is obscured and the goggles are no good anymore, right? So the greater the depth, the better the goggles, right? So that's kind of obvious, right? That means that the goggles do not leak until greater depth, and therefore they're of better quality. So the data are recorded in the file Thorndike. Here is the question: can we conclude that Thorndike, the contender, offers a better quality goggles than OptiView? Okay, interesting question. All right, so let's turn our attention, of course, to our software, RStudio. Okay, so Olympic goggles problem, right? Okay, problem. All right. So first things first, right? Goggles data. That would be read from the CSV file, and I already downloaded. C drive, data folder, Thorndike.csv. Okay, so there it is. Alright, let's take a look at the structure, right? Not required, but kind of a good idea. Goggles data. Alright, so what does it say? It says that there are 50 observations in two variables. So, in other words, I have actually, and let me show you the same exact file actually in the in Excel. Alright. So Thorndike right there. Alright, there it is. Okay. So here's my sample number 1, Thorndike. I have 50 observations. And here's my sample number 2, the OptiView, right? The competitors. Sample sizes are the same, I want to point out, right? Obviously, when you have matched pairs, right? Matched pairs is what? Observation from sample 1 matched with exactly one observation from sample 2. So when I have matched pairs, right? That's the first question that I have to ask myself. Actually, you know what? Let's be meticulous about that. Let me not jump the gun here. Let's go back to the analysis flowchart. So in this problem, I'm going to start with this starting point, right? I'm comparing two populations, right? Thorndike versus OptiView. What is the data type? Well, numbers, right? So numerical interval data. Descriptive measures, do I look at central locations or do I look at the variability? Well, we never look at the variability in this course, so I'm looking at mu, right? Central locations. Next question. What do you have? Experimental design. Are samples collected independently or are samples collected as matched pairs? Well, here I'm tempted to say that since the sample size is the same, 50 from one and 50 from another, these are matched pairs, right? Each observation from line 1, number 1 from Thorndike, matches the observation from the OptiView, first pair of goggles, and the other first pair of goggles. No. Actually, for these goggles to be matched pairs, there should be something in common between them. I don't know what it can be. It's just basically one pair of goggles from manufacturer number 1 and completely different pair of goggles from the manufacturer number 2. So the fact that the samples have the same size, 50 and 50 in that case, doesn't mean anything really, okay? Doesn't mean that the samples are matched pairs. So for the samples to be matched pairs, there should be something else. Something that matching precisely these two numbers. So, in other words, this pair of goggles and this pair of goggles, they should have something in common. And that something should be different from the next line. And it should be different from the next line, okay? The fact that, essentially here's the deal, right? We get a box of Thorndike's goggles. We just put it on 50 dummies and drown them. And then we get another box from OptiView. We put them on dummies and again drown them in the water, right? That's it. So these pairs of goggles, they have nothing to do with each other. They have nothing in common, right? They come from different manufacturers. Samples are collected independently. So coming back to my flow chart, I'm dealing with independent samples. All right. Now, next question is, are populations distributed normally or non-normally? And that comes back to the point that I was just discussing, right? That if you have independent samples, and we do have independent samples in this question, we have to check both samples separately for normality. So let's go ahead and do that, right? So Thorndike sample. Okay, normality. Alright. So first of all, let's look at the histogram, right? HIST for the goggles data. Or goggles data. Alright. And the column Thorndike. Bam. Not too bad. It appears that there might be some, peak 1, peak 2, right? So it's bimodal data, but not really. It's probably just a random fluke, okay? Because sample is, 50 different observations. Due to the randomness, you can see things like that, okay? So it's not a huge valley, so that's probably not an indication of non-normality. So let's run the Shapiro test, right? Shapiro-Wilk test, and exactly same thing. Goggles data for the column Thorndike, and there it is. So again, the rule of thumb is I'm looking for high p-values, right? If p-value is high, that means that my null hypothesis stays, and null hypothesis always for the normality test is data are normally distributed. So what do I see? P-value is 0.63, enormous, huge p-value. Of course, it's higher than any reasonable significance level that I can pick, and we agreed that for the normality test we will always use 5% significance. 0.63 is greater than 0.05, therefore null stays. Data are statistically normally distributed. So first sample is good to go. How about the second sample? I'm gonna say OptiView normality test. Okay. And that would be again, let's go with histogram, right? So same, goggles data. And the column is now OptiView. Well, that's actually pretty nice, right? Fairly normal looking. Okay. Now how about Shapiro test? Goggles data, OptiView. Alright, so here is my p-value, 0.36. Again, it's higher than 0.05. Therefore, I failed to reject the null. And my null states that the sample is normally distributed. Okay, so I have a green light, right? So what does my flowchart say? Alright, so I was here, right? Interval data, central location, independent samples, normally distributed data. Now I'm good to use t-test for mu1 minus mu2. So now let's go ahead and formulate actually our hypothesis, ladies and gentlemen, right? What exactly is that we're testing? Okay, so here is what, so independent samples, right? Both samples were not pre-cooked, so one pair of goggles is not hand meshed with another pair of goggles, hence we have independent samples. Alright, so we did the normality test for sample 1, for sample 2. Here's what we're testing, right? The goal of the study, right? Let's go back to the problem, right? Can we conclude that Thorndike offers better quality goggles? Better quality means that they don't leak until bigger depths, right? So therefore the average, here's my hypothesis, right? If I'm claiming that Thorndike goggles are better than OptiView, that means that the average depth for leaking for Thorndike is going to be higher than the average depth for leaking for the current supplier OptiView, right? So mu Thorndike is higher than mu OptiView. But remember that each time when we test hypothesis about two populations, it has to be recorded in the form mu1 minus mu2, right? So, and that's exactly what I'm going to do. If first average is higher than second average, that's my hypothesis, right? I can just simply subtract the second average from both sides. I'm going to get that the difference is positive, right? First is higher than the second is the same thing as to say first minus the second is greater than 0, right? So therefore my hypothesis that the average for the Thorndike is higher than the average for the OptiView is the same thing as average for Thorndike minus the average for the OptiView is greater than 0. So that's what I'm testing. Now, therefore, null becomes opposite of the alternative, right? Mu1 minus mu2 less than or equal to 0, right? But the important thing to remember is that I pick Thorndike first, right? It's going to be important in just 1 second when we're going to actually do the testing in R Studio, okay? So, my mu1 is Thorndike, my mu2 is OptiView, and the alternative has the form greater than. And the mean for the mu1 minus hypothesized mean, mu1 minus mu2 in my null is 0, right? So these are 3 things that I have to remember. Now let's actually remember how I use this cute analogy. If there is a fire, there should be a smoke, right? We suspect that the average leaking depth for Thorndike is deeper, higher than for the OptiView. Well, if that is true for the mean, that probably should also be visible from the samples, right? For the population means, that also should be visible from the sample means, right? So let's go ahead and find out mean for Thorndike, for the sample, right? Everything that we do from that point on is about samples, right? But hypothesis testing is about population means. Okay, so mean for Google data Thorndike is how much? 93.7, whatever that is, meters or feet, right? 93.7. That's on average how deep the goggles are submerged when they start leaking the water. Okay, so how about the other one? Mean for goggles data OptiView is 88.9, roughly speaking, right? So we can see, let's say these are meters, right? We can see that Thorndike holds the water about 5 meters more, on average, of course, right? Compared to the current supplier. So it seems that our hypothesis, alternative hypothesis, that is, right? It has some sort of the confirmation, okay? Because the samples suggest that the average leaking depth for the Thorndike is higher than the average depth for the OptiView. So there might be some truth to the fact that Thorndike glasses hold water better, right? But again, we have to test the hypothesis, right? Again, because of the variability, okay? There may be no difference between these two, okay? And the fact that this sample, Thorndike sample, had higher average could be purely because of randomness, right? We just happened to get 50 better goggles than from Thorndike than 50 goggles from the OptiView, purely randomly. Could that be accidental? Yes, it could, right? Our job here is to find the p-value, right, or the likelihood. How likely is that to see that big of a difference, about 5 meters between them, right? If one is not really better than the other, right? How likely is that to see that big of a difference if null is true and Thorndike does not supply better goggles than the OptiView, okay? That's essentially what p-value is. Alright, so for that we're going to use precisely the same, and I've put that in the hypothesis testing in the slides right here, okay? We're going to use precisely same function as I told you before, t-test, right? The only thing is this: when we discussed one population test, the first argument that we supplied for the function was your column of data, right? Well, in this case we're going to supply 2 columns of data, okay, because we're testing 2 columns, right? But here is what's important, okay? Remember how I recorded the hypothesis? My first mu1 was Thorndike, and my second mu2, which I subtracted, right, was OptiView. I have to supply these columns of data to the function t-test in exactly the same order. So in other words, whatever I pick the first in my hypothesis and whatever I pick the second should match how I perform the test, okay? Because I could have recorded the same hypothesis differently, right? Mu Thorndike minus mu OptiView is greater than 0 is exactly the same as to say mu OptiView minus mu Thorndike is less than 0, right? I could have picked OptiView to be first, right? Doesn't really matter, okay? But once I picked certain form of the hypothesis, both null and alternative, right? Which one goes first and which one goes second, that's exactly the order how I should supply the columns to my function t-test. So Thorndike should go first, OptiView should go second, and after that, for the mu, I have to provide that value, whatever my hypothesized difference is, stated in the hypothesis, and then the alternative form, right? And again, there are three alternative forms, right? Your alternative can be either greater than, or less than, or simply not equal for the two-tailed test, right? For the two-sided test. Okay, so in this case, I have alternative to be greater than form, right? Okay, so let's go back. So t-test, right? Where's my punchline? Here. Right, t-test for difference mu Thorndike minus mu for OptiView, right? All right, so I'm gonna say t dot test. All right, and the first one comes Thorndike, so it comes from Google's data column Thorndike, comma, second column is Google's data $ OptiView. The hypothesized difference mu1 minus mu2 is 0. By the way, doesn't have to be 0. I believe in the next lecture we're going to take a look at the case when I can actually test, for example, is that true that Thorndike is at least 5 meters better in terms of leakage than the OptiView, that kind of stuff, right? So it doesn't have to be 0. In this case, yes, it does happen to be that the difference, hypothesized difference is 0, but it can be anything real, okay? And my alternative form is, oh god, what was it? Greater, right? Thorndike is better, so therefore leakage is greater, the difference is positive, so therefore greater than 0. Okay, so I run this line, and you can see that first of all it gives me the same point estimate. Mu for x, the first one is 93.7. Mu for y, the second one is 88.88. And the p-value, to see that big of a difference or more, if the null is true and there is no difference between them, is 0.0373. Okay, is that the same that I put in there? Just out of curiosity. 0.0373, right? Okay, so what p-value? So now we have to kind of decide which hypothesis stands, right? What p-value do we use? Is there anything in the problem that says use 10% or 1%? Nothing, right? It just says, are the Thorndike goggles better in the quality than OptiView? Okay, well, let's see. Let's use p-value standard, right? Not p-value, sorry. Significance level, right? So, using standard significance level, our p-value 0.0373 is less than 0.05, right? So my p-value is less than my significance. P-value is less than my significance level. What happens each time, always, when my p-value is less than the significance? I have enough evidence, so this is small probability, right? It's unlikely to see that big of a difference if goggles are really not different, if the difference between them doesn't exist. So therefore, that means that this 5 meter difference in terms of x bars, right? X bar 1 minus x bar 2, it is actually a pretty rare event to see by accident, okay, if there is no difference. So we have to reject the null hypothesis. P-value is less than alpha. Reject the null hypothesis, and what do we say? Our alternative says that the difference between them, so let's go back, right? Our alternative right here says that difference is positive, or in other words, Thorndike statistically leaks at larger depths than OptiView, right? So that's my kind of statistical answer, right? I have enough evidence in these samples to reject the null hypothesis in favor of alternative hypothesis, right? So therefore, since this is my statistical answer, we reject null in favor of alternative. In business terms, that means that the average leaking depth for Thorndike is statistically higher than the average leaking depth for OptiView. And what does that mean in terms of executive decision? the Olympic Committee should switch their current supplier of the swimming goggles from their old company OptiView to the new contender Thorndike, because in the standard leaking test their goggles proved to be of higher quality. End of story. Alright, so this is the end of this lecture. I went about 15 minutes over my self-imposed limit, but I guess that's okay. So in the next lecture we're going to take a look at example when the data, numerical data again, are collected from matched pairs. Okay?